We're ready to start with our first talk, which is going to be given by Lia Corrales, an assistant professor at the University of Michigan, talking about new opacities for hazes formed in different C2O environment. So Lia, take it away. Is everything working?
Sorry, I forgot to unmute myself. I'm ready now to share. Okay. Let me know if you see any issues.
Looks good.
Okay, great. Thanks very much. Thank you to the organizers and whoever swapped spots with me. By the way, I really appreciate you dealing with my hectic schedule. I'm here to talk about some recent work that was just published in AppJ Letters, and that is we're releasing new opacities for hazes formed in different C2O environments. So why are hazes important? Well, we know that hazes can affect the climate and habitability of terrestrial planets. For instance, early Earth, just 3 to 4 billion years ago, was believed to be potentially haze dominated at certain times and not others, based on a methane-filled atmosphere, which would have been created by methanogens. And so the spectrum and the absorptivity of an early Earth would be very different from modern day Earth today due to hazes and other things. We also believe that hazes can obscure interesting molecular features in cool planets. One of those planets is the sub-Neptune GJ1214b, where a particularly flat HST spectrum has given evidence that clear atmospheres just don't work. And there are a number of works that have been investigating the role potentially of haze formation, which is a photochemical reaction, in order to explain this super flat line. And in our solar system in particular, we have a hazy moon Titan around Saturn, which has been a test bed for haze chemistry and is particularly interesting because it has an atmosphere. It's the only other body in our solar system that has an atmosphere remotely similar to Earth, meaning that it's dominated by nitrogen. And it has a similar surface pressure. So there's been a lot of work done on haze formation in Titan. So for instance, there's the canonical work by Corrales et al. In 1984, where they grew hazes in a laboratory, which we call tholins, and produced optical constants for those tholins. And those are in use today in many of the simulations where people are trying to understand how hazes can obscure exoplanet atmospheres. There is a limitation because this one template was grown in an oxygen-free environment, which is what Titan is like, and it's applied widely in the field. So our goal is to provide more options for including hazes in simulations of exoplanet atmospheres. And in particular, there was recent work by Gavilan et al. In 2018, where they grew tholins in different CO2 to CH4 environments. It's still an N2 dominated environment like Titan, but we've added some different carbon and oxygen bearing species, giving us a rough sense for a C to O ratio and how that affects the growth as well as the absorption properties of tholins. So these absorption properties were measured from about 0.13 microns all the way out to 10 microns with a variety of techniques, both ellipsometry and direct transmission. And our goal was to take these measurements, apply Kramers-Kronig so that you can get the complex index of refraction, which is what you need in order to do all the absorption and scattering portions, and then calculate opacities and insert these new haze species into transmission spectrum simulations. And as a bonus, we are looking to see if some of these hazes can have spectroscopic signatures that give us a clue to the C to O ratio environment for those transmission models. So like many others, we've chosen GJ1214b as a test case. And on the left, you see what our transmission spectroscopy simulations look like. On the right, you see the vertical haze profiles that we used from Kawashima and Ikoma. They have a prescription for a theoretical prescription for growing hazes photochemically, and they did a whole bunch of simulations for GJ1214b under a variety of C to O ratio, metallicity, UV, irradiation, and other scenarios as well. So they gave us some really nice templates to work with. And on the left, you'll see we used the Corrales et al. Hazes to make the peach line. And then, oh, this does work, okay. We made this peach line with Corrales hazes in our simulations, and then the dashed line shows what Kawashima and Ukuma did. And they also use the Corrales hazes, which again is becoming a standard in the field. And this is a simulation where we had solar-based C/O ratios. So here you see our new models with a solar-ish C/O tholins, and it's quite different. In fact, it's about 200 ppm different. So that's like kind of the summation of the result. I'll show one more slide just talking about the science impact, but this is really about the code. So I just wanted to say there were a few things that went into this. First, in order to add hazes to the model, we were using the exotransmit code, and we're using a major refactor of that exotransmit code, which was done by Thiel et al. In 2022. This is part of the Kempton group. So this new exotransmit code, you can directly import vertical profiles of chemical abundances, whereas the original code used a 2D pressure temperature grid of volume mixing ratios, and it was in these EOS files, whereas the new version doesn't use those. And then the other major upgrade is that you can now add opacity tables and vertical profiles complementary to these N and S profiles that you see here. And you can just directly add your aerosols as opposed to simply using parametric gray cloud or Rayleigh scattering prescriptions. So that's a huge upgrade. And I just want to say that this was all powered by open source collaboration on GitHub. So I was working from Thiel's code directly there, sending issues and pull requests and things like that. However, there was a bit of a problem. These are branches developed on branches in GitHub, and because it's such a major change in the baseline exotransmit code, I didn't really feel comfortable suggesting that we do a huge pull request into the main exotransmit GitHub library, because then the people who are using it, such as the PI, wouldn't be able to use it with the code they've been using all along for probably years. So this version of exotransmit is released as static code on Zenodo, along with all of our data products, including the opacities and complex index of refractions. Okay, so what's the bottom line impact? We do get this really strong feature around 5.8 microns for solar-like C/O tholins. Again, it's like a 200 ppm case for hydrogen helium dominated atmospheres, and much less if you have a very depleted hydrogen and helium atmosphere. That's the bottom line. I want to talk about the database and the source code. So if you go to this DOI, this is everything that we have. We have the source code for calculating cross sections, which is based on my open source library on GitHub. So it's github.com/ebler/newdust. It's just a really fast scattering algorithm. And we have all the base code that was used to calculate the opacities for exotransmit. We also have the source code for exotransmit and the opacity data. The refactored exotransmit code has 2 new folders to it compared to the old one. We have the vertical haze profiles that were used in our work and just examples of how to input hazes, as well as the actual cross sections and ASCII format in the folders here. We've also released just ASCII format tables that include the attenuation efficiencies and G factors. So for each different C/O ratio that we used, we have the scattering efficiency, extinction efficiency, absorption, as well as the G factor, which tells you whether it's forward scattering, back scattering, or isotropic. Oh, come on. It stopped scrolling, 1 second. There we go. Okay, and then finally, because there's many codes that will directly take the real and imaginary values for the complex index of refraction. Sorry for the, oh, I don't know why that happened. Okay, sorry. There we go. We also have ASCII files that just give you those raw values as well. So we're hoping that this is the most convenient form for most people who want to incorporate these hazes, but I'm also here to ask if people need it in a different format. So please feel free to message me on Slack or ask questions at the end. So what are the science use cases for this? In particular, it can help connect the UV to the infrared because these cross sections go down all the way to 0.13 microns. They don't go past 10 microns though. Because these tholins were grown in a nitrogen dominated atmosphere, they're technically more physically ideal for terrestrial planet models and assessing habitability. But nonetheless, people have been using opacities from tholins grown in a nitrogen dominated atmosphere. So if you are, not doing terrestrial planets, this is just another option compared to Correa. And in particular, it demonstrates that we can really look for infrared haze features to constrain the composition of the atmosphere. So even if you have hazes, you're not going to have a dead spectrum. And then I would just like to point out that this is actually one of several new opacities coming out. So there's some new hazes out from the Hearst lab that gives us optical constants of for the JWST wavelengths as well. And they get similar sort of profiles and a few interesting features as well in the infrared. So I would just like to say, have fun with hazes. Here's the information for both groups, open source data and databases, and I'm happy to take questions. Thank you.
Awesome. Thanks a lot, Leah. This is great. I certainly have questions, but I just want to see, so we don't have questions on Slack yet. If people have questions here in WebEx, you can raise your hand. Otherwise, maybe I'll kick it off. So I think it's really great that we can do this, and I guess it's probably something that you would think of using more for forward modeling than for retrievals. I'm actually curious. So the way I see it right now, the measurements have been made for a few fixed C/O ratios. And so I guess it's probably not accurate to just like interpolate between those because there are like different chemical reactions happening. Do you have an idea in terms of the interpretation of observations using these new refractive indices and everything that you're providing? Would it be more calculating transmission spectra for the different C/O where we really have measurements and seeing if some features match rather than trying to exactly fit the data? Yeah.
Okay, so I think if I understand your question completely, you're basically asking like, how do we interpolate between different C/O ratios, or like what's the next level of complexity? So I'll go back to the Gavilan work because she did a really amazing job breaking down like where a lot of these features were coming from. So as we go to an increasingly oxygenated atmosphere, we see an enhancement in these essentially what are CO bonds in the tholins. So that's just representing a greater uptake of oxygen in those tholins. And by the way, the y-axes on these two plots are not the same. So these ones are a few times stronger than these, where you have no oxygen in the environment. So I think that's one way we can start to think about interpreting these features, but there's definitely more work to be done because the Gavilan tholins in the 2018 work, there was the solar ratio was actually kind of quite interesting compared to the other ones, and there wasn't really a continuum. The story that we've put in this particular paper does look like a continuum, but there was one measurement that was kind of between solar and C/O of 1 that isn't so close to the C/O solar and is like a little bit closer to 1 in kind of some weird ways. So it's not always that easy, but I think it's definitely something to continue investigating. And like I said, thinking more carefully about kind of the molecular features and how they turn into solid state features in the infrared.
Okay, awesome.